Hello, this is week 9, lecture 2, energy in rotation. So this is coming from different parts of a few chapters because I kind of just wanted to put all this rotation rolling stuff together. So it's 9-7, 11-7, and 12-4. And we're going to talk about rotational kinetic energy, rolling motion, and then we're going to do sample problem 12-8 and then an example of a rolling ball. So I'm not going to drive these for you, but work, power, and kinetic energy in rotational motion. So work is the torque times the angular displacement. Power is the torque times the angular velocity. Remember, these are just like the linear versions because that is work in linear is force times displacement, and power is force times velocity. We have the same kind of thing going. And then for rotational kinetic energy, it's 1/2 I omega squared. So 1/2 the moment of inertia times the angular velocity squared. Now, I want to talk a little bit about rolling motion with this. So in rolling motion, well, let's just look at this. We have these two parts of this wheel. The yellow line is showing this motion of the center of the wheel as it rolls, and then the red is showing like the rim. And you can see that they travel different distances. Like because the wheel is spinning along with rolling, a part on the edge is going to move more of a distance than a part that's just in the middle. What this looks like is translational motion plus rotational motion to give us rolling motion. So in translational motion, we ignore that there's rotation and every part of it is just moving with the same linear velocity. In rotation, we kind of ignore the translational motion and we just have the same angular velocity throughout. And if we're looking just at the edge or the rim, it's omega r because that's what, like, an r being the radius, because that is also equal to the velocity of the edge. And then the center isn't rotating. And one thing to note with this is when we combine these, on the top, we end up with double the velocity because it's spinning and moving translationally. In the middle, we just end up with the velocity from before because, again, in rotation, it wasn't moving. But then the bottom part of the wheel has no velocity. And this is because there's the translational motion to the right and the rotational motion to the left, and they cancel out. And you'll see this, I don't have a picture for you right now, but you can see this in pictures of like a bike wheel or just a wheel in motion. You'll notice that the part touching the ground is not in motion while the rest is. Like those parts of the picture will be blurred while that part isn't. So this is how we describe rolling motion. And because of this, because this is different than both like separately translational or rotational motion, we have to think about kinetic energy a little bit differently. So I literally just gave you this definition, but we have to think about things a little differently because when something is rolling, its pivot point is not the center, it is the part that is touching the ground, which means we have to do parallel axis theorem for the moment of inertia. So we have the moment of inertia of the center of mass, and then the total mass of the wheel and the distance from the center of mass to the pivot point, which is just the radius here. So we end up with this as our moment of inertia, or sorry, rotational inertia. And we can plug that into the kinetic energy equation, and we end up with 1/2 the rotational inertia of the center of mass times the angular velocity squared plus 1/2 times the total mass times the radius times the angular velocity squared. And this is also actually just the linear velocity. So here it is, written in more familiar form. And what we end up with is that for rolling motion, we have the rotational kinetic energy, so 1/2 rotational inertia angular velocity squared, plus the kinetic energy of the center of mass, which is kind of our translational kinetic energy that we're used to. So when we're dealing with rolling motion, because we have translational motion and rotational motion happening, we have to think about things slightly differently. So we're going to do a couple example problems that take this into account. So first, we want to use energy to find the speed, the angular speed, I believe, of this cylinder at the bottom of this incline. So yeah, let's do that. Okay. And one thing to note with this, the initial velocity, we're assuming it's starts from rest. So the energy of our system, the total mechanical energy, is the kinetic plus the potential. And energy is conserved, so the final equals initial. Initial energy is the initial kinetic plus the initial potential. But I just said the initial velocity is 0, so there's no initial kinetic. And then the initial potential is just mgh, because h is our height here. And then for our final, kinetic final and potential final, but when it gets to the bottom, the height is 0, so this is 0. So that just leaves us with the final kinetic, and this is where we bring in what I just showed you, that the final kinetic is then, because it's rolling, 1/2 the rotational inertia of the center of mass, the angular velocity squared, plus 1/2 the total mass times the velocity of the center of mass squared. So this is a cylinder. So the rotational inertia of the center of mass of a cylinder is just 1/2 mr squared. And then the other thing I'm going to say, yeah, sorry, when I was describing this problem a moment ago, I said that we were finding the angular velocity at the bottom, but I think we actually want the regular translational velocity, but really we can just find both. It's fine. But in order to do that, I'm actually just going to plug in that the angular velocity equals the velocity divided by the radius. So I'm going to plug that in here, 1/2. First, the equation for the rotational inertia, 1/2 mr squared times b over r squared plus 1/2 m, this is bcm, bcm squared. So we get some stuff that cancels. The radius squared cancels. Okay, that's all that cancels. And we end up with 1/4 m bcm squared plus 1/2 m bcm squared. And we can combine those. And we get 3/4 mv center of mass squared. So that is the final energy. And the initial is this mgh. So we know that energy is conserved, so we can just set these equal to each other. Mgh equals 3/4 mv center of mass squared. Those are the same mass, and they're on both sides, they cancel. And then we're just gonna solve for the velocity of the center of mass. So that means dividing both sides by 3/4 and taking the square root. So what we end up with is 4/3 gh square rooted equals the velocity of the center of mass. And as I said, we can also find the angular velocity. That's just the velocity divided by the radius. So the angular velocity is 1 over r times the square root of 4/3 GH. So that is that problem. And so it was just conservation of energy. Initially, there was no kinetic energy, and then in the final, there was no potential energy. We used our rotational kinetic. So now let's do this other example problem of a rolling ball. So we have a ramp on a table, and there's a ball at the top of the ramp, and it's going to roll down and then off of the table. And we want to know how far it falls from the table. So we have the mass of the ball, which is 0.025 kilograms, the radius, which is 0.01 meters, the height of the ramp, which I do want to say in this diagram, the height is not to scale because the height of the ramp and the table in my diagram are very similar. They are not, because the ramp is supposed to be 12 centimeters and the table is 1 meter. And yeah, so we want to find the resulting displacement. So let's write down some stuff. It starts at rest. And this one is a sphere because it's a ball. So the rotational inertia is 2/5 mr squared. And yeah, we'll call these points 1, 2, and 3. So the energy at 1 is kinetic energy at 1 plus potential energy at 1. But the velocity starts out at 0. So this is just mgh, which is the height of the ramp, plus the height of the table. And then the energy at 2 is kinetic at 2 plus potential at 2. Let's see, hopefully I have enough room. I'll try and write smaller. So this is where we have to take into account that we're rolling. So it's 1/2 I omega squared plus 1/2 mv squared, and then plus mgy, so height of the table. And these are equal to each other, so we'll set them equal. mgh plus yt equals 1/2 I omega squared plus 1/2 mv squared plus mgy. Okay, 1 second. Okay, now we can plug in for the rotational inertia and cancel some stuff out. So mgh plus yt equals 1/2 times 2/5. I guess it's lowercase m now, mr squared times, I think I'm also gonna plug in for omega, just b over r again, b over r squared plus 1/2 mv squared plus mg yt. Okay, so everything has mass in it, so we can cancel that out. And then, oh, there's more stuff we can cancel. We can also cancel out that radius, and then there's 2 on the top and bottom there. Okay, let's take a look at what we've got. Got g times h plus yt equals to 1/5 velocity squared plus 1/2 velocity squared plus gyt. So we want, I guess I didn't tell you what I was doing, but if we want to know how far it gets from the table, we really need to know what velocity it launches with. And so that would be the velocity it leaves the table with. So that's what I'm trying to find. I guess I kind of skipped that step and went straight into conservation of energy. But honestly, with energy problems, when you know energy is conserved, it's okay to just start doing it. Although at one point you should like stop and think about what you're actually looking for. So I'm gonna just solve for velocity. I'm gonna subtract dyt from both sides, which just ends up on canceling it on that side. So we have gh equals, factor out v squared, and I have 1/5 plus 1/2. This is 2/10 plus 5/10, so 7/10. And I'm going to divide that on both sides and then square root. And so we end up with 10/7 square root gh equals the velocity. And we can plug in our numbers. Square root 10 divided by 7 times 9.8 meters per second squared, times 1 meter for the height. Oh, wait, sorry, not that. Times 0.12 for the height of the ramp. There we go. And this gives us a velocity of 1.3 meters per second. So that's that part. We use conservation of energy, and then and the fact that it was rolling. And so we have the velocity, and then we can just do kinematic at this point and use because it's projectile motion and we're just launching it. So we need to know the time it takes to travel that distance in order to know how far it travels with the speed. So maybe it's been a minute, but in projectile motion, we find the time usually with the long kinematics equation in y. That time is not squared plus 1/2 ayt squared. So the final velocity, or sorry, final position is on the ground. So this is 0, and it only has velocity in the x direction. So this is 0. So we end up with 0 equals y initial plus 1/2 ayt squared. We want to solve for that time. I'm going to skip some of the algebra steps and just tell you what it is. It is negative 2y initial divided by ay, which is negative g. So we can plug things in, square root, those negatives cancel, so it's 2 times 1 meter divided by 9.8 meters per second squared, and that is 0.45 seconds for the time. And then we can find that distance because it's just going to be velocity times time. Our velocity is 1.3 meters per second, and the time is 0.45 seconds. And that gives us 0.59 meters for the distance. So I want to also just quickly show you something. So if we had ignored that it was rolling, that would mean our energy would look like mgh plus yt still, and then mgh or mgyt, but then the kinetic energy would just be 1/2 mv squared. And doing the algebra there, the velocity would be the square root of 2gh, which is 1.5 meters per second. So that's faster. The time would still be the same because that didn't include the rolling energy stuff. So time is the same, the velocity is more, so obviously it's going to travel farther. Second, and this is 0.69 meters. So what we find is if we don't include the fact that it is rolling, we will assume that it goes 10 centimeters farther than it actually does. Um, so yeah, important to keep that into account because it changes how fast it's going and therefore how far it goes. Yeah, that's all for this lecture.